Fourier series. And just to remind you, the main things that we're dealing with in Fourier series is, well, this is what they look like. It's a way of representing a not completely arbitrary function, but a nice, relatively well-behaved function can be represented on the interval pi between minus pi and pi by an infinite series of this form. There might be some constant, some basic setting level of the function, which is this half a0 term at the front. Then you've got an infinite number of cosine functions, cosine nx for each n between each integer multiple n of x. And then a similar infinite series, but this time using the sine function, sine nx. This is valid in the range minus pi to pi. And this equals relation holds everywhere that the function is continuous. And maybe just as a caveat, it's equal to a half times the left-handed limit, all this y, plus the right-handed limit fy. So this is the average of the left and right-handed limits. The left and right-handed limits at points of discontinuity y. Okay, so everywhere the function is continuous, you get this exact agreement. But places where the function is discontinuous, the Fourier series is this nice fair value equal to the average of the left and right-handed limits of the function as you approach that point of discontinuity. F minus being the limit of f of x as x approaches y from below, and f plus as x approaches y from below. So so then the question about what the Fourier series is becomes a question about what these Fourier coefficients are. And these are all given by nice formulae, which you can consider them as integral formula in terms of integrals, but these are also understandable as inner product formulae. So the inner product of the constant function 1 with the function f under consideration, rescaled by 1 over pi, this gives you the constant coefficient a0 from the Fourier series. The other an's are the inner product, the integral of the function f of x times the corresponding basis function, cosine of nx, which itself is the inner product of cosine of nx with f of x. And a very similar formula for the bn coefficient, but this time featuring the sine basis function. Okay, so that's the basic nuts and bolts of Fourier series that we've looked at up to now. We've looked at a few actual Fourier series for specific functions f. We've looked at the square wave function, or otherwise known maybe as a Heaviside step function, the function which is 0 on the negative half of the interval and +1 on the positive half of the interval. We've looked at the Fourier series of the function f of x equals x. And some of you in the tutorials might have been looking at x squared. We'll also take another look at x squared today. We did justify those coefficient formulae somewhat by, we gave an argument motivation or justification argument for them, but based on the existence of the Fourier series. If we accept that the Fourier series exists, then using the linearity property of the inner product and the orthogonal property of the family of basis functions. Remember, we proved in the lecture and tutorials that the basis functions, all the cosines, all the sines, and the constant function 1, they are an orthogonal family with respect to the inner product. Meaning, if you take any two of those functions, take their inner product, you're going to get 0, unless you're taking the inner product of a function with itself. Okay. In which case, you got pi all the time. And that explains the rescaling by 1 over pi here at the front of these inner product formulas. Okay, then, so what's on the cards for today is to consider what the Fourier series of certain symmetric functions look like. So this is section 3.3 in the notes. Now, what do we mean by symmetric functions? Well, when we consider functions in terms of their graphs, there are two, especially since we're dealing with the cosine and sine function, there are two ways in which functions can be kind of symmetric, or there can be some clear relationship between its behavior on the positive half of the interval and its behavior on the negative half of the interval. Okay. So this is even and odd functions. So a function f, we have this definition that a function f is even if for every argument x, f of minus x is equal to f of x. And a function f is called odd if for every x, f of minus x, the minus sign kind of comes out. For even functions, the minus sign in the argument makes no difference. For odd functions, the minus sign in the argument pops out. Now these are, a function has to be quite special in order to be even or odd. So, like, what's the typical graph of a even function looks like? Well, whatever its behavior it has on the positive half of the interval, because f of minus x is always equal to f of x, its behavior on the negative half of the interval must be the exact mirror image of that. Yeah? So I'll attempt to draw that now. So it kind of waves a bit up there, and it comes down, and goes up again, down again. Okay? It's a terrible picture, but it does convey the behavior that whatever it does on the right-hand side, it's doing the exact mirror image of it on the left-hand side. Whereas, so that's an even function. An odd function, let's draw the same kind of behavior on the right-hand side. If an odd function is doing that to the right of the y-axis, well, f of minus x must be the negative of what it's doing. So in order to draw it on the left-hand side, less than 0, you have to reflect it like we did for the even function. You have to reflect it in the y-axis, but then immediately reflect it in the horizontal axis as well, because it has to have a negative behavior. So we have to swap the positive y with negative y. So the behavior of the odd function down here would be something it's even worse picture, but everybody appreciate what I'm trying to show? That the behavior on the left-hand side is obtained by taking the behavior on the right-hand side, reflecting in the y-axis to move it into the argument minus x, but then because the function is odd, it has to have a negative behavior, so you have to flip it in the horizontal axis, flip positive y with negative y. So if you look at example 3.6, so cosine and sine fit into this family very nicely. The cosine function is even. The cosine of y is always equal to the cosine of negative y. The sine function is odd. As if you try to evaluate sine at negative y, it will be the negative of whatever value it has at y. And the polynomial terms, single polynomial terms, g of x equals x to the n. So some of these are even, some of these are odd. And they're even or odd depending on what n is. So this is even for even n, and it's odd for odd n. So this is perhaps where the terminology comes from, but it's not the same definition. Even integers, which is on to the right of the comma, even integer n, odd integer n, that's to do with being divisible by 2 or not. But even function, odd function is to do with it behavior left or right of the origin, x equals 0. But there is this connection between the two terms when you consider the integer power of the argument x. Example 3.6 poses the question, is there a function which is both odd and even? Well, it says there is one function that's both odd and even. 0. Yeah, the constant 0 function. It's not an interesting, genuine example, but rather kind of a trivial example. The constant 0 function, z of x equals 0 for all x, okay, is both even and odd. Both even and odd. No other function is. No others are. The only way you can be equal to plus something and minus something is if it's equal to 0. But you do have to be careful every time you introduce kind of definitions into mathematics that look like opposites. You always just have to be very careful and think, well, of course, they're not opposites, because like a typical generic function you encounter is not going to be even or odd. Okay, it's special symmetric behavior either way. If you look, there's a subject called topology, which is a generalization of calculus, kind of. And in there are technical terms open and closed, which are great terms, and you build up an intuition about them. But unlike door is either open or closed, but in topology things can be open and closed. So you have to be careful with reusing words and kind of commonly understood words. All their properties aren't always replicated in the mathematics. Okay, theorem 3.2 is kind of along those lines. Theorem 3.2 is about the multiplicative properties of such functions. what are the multiplicative properties of these functions? Well, f1 and f2 are even functions. g1, g2 are odd functions. Okay, we can form product functions. If you multiply together two even functions, you again get an even function. If you multiply together two odd functions, you get an even function. And if you multiply together an even function with an odd function, you get an odd function. So this is potentially very massively confusing because even and odd integers don't behave like that multiplicatively. If you multiply together two even integers, okay, you get an even integer. If you multiply together two odd integers, you get an odd integer. If you multiply together two odd functions, you get an even function. If you multiply an odd integer by an even integer, you get an even integer. This is divisible by 2. But when you multiply together one even function and an odd function, you get another odd function. So actually, this is replicating the additive structure. When you add the additive properties of even and odd integers. Okay, if you add two even integers, you get an even integer. If you add two odd integers, you get an even integer. If you add an even integer and an odd integer, you get an odd integer. Okay, you can comprehend or appreciate that connection between the multiplicative functions, the multiplicative properties of the functions, and the additive properties of the even and odd integers, because that, if you think about multiplying together these polynomial terms, when you multiply together two powers of x, what you're doing is effectively you're adding the exponents. Yeah. So this connection between even and odd integers as the exponent on an x, producing an even or an odd function, then the multiplicative property of the function, multiplying these functions together, that's the same as adding the exponents. The exponents are the even and odd integers. That's why this feature over here is replicated in adding the even and odd integers. But it's just potentially kind of confusing because you're reusing the words even and odd for kind of different things, and there's a connection between them, but maybe with a little bit of a twist. Okay. Now, does theorem 3.2, does it require much of a proof? No, it doesn't require much of a proof at all. For example, let's take the g1 times g2. We multiply g1 times g2 times an argument minus x. Well, by definition of what it means to multiply together functions, this is g1 of minus x multiplied by g2 of minus x. Yeah. It's just the definition of what it means to multiply two functions. But g1 and g2 are both odd. g1 and g2 stand for odd functions. So g1 of minus x is minus g1 of x. g2 of minus x is minus g2 of x. Well, you've got two minus signs in the product there, so they cancel out. You're just looking at g1 of x times g2 of x, which is, of course, the value that the product function g1 times g2 takes on x. So there you see it. The product function g1 times g2 is an even function. Okay, because it doesn't care whether you're considering x or the negative of x. It's going to give you the same value. So the proof is just tracking the location and behavior of the minus signs. It's the same kind of argument for any of the other two cases there. Multiply the f1 times f2, or multiply the f1 times the g1. Similar for other cases. Similar for the two other cases. Now, why are we introducing Why are we introducing these concepts of odd and even function? The reason is that their Fourier series have nice properties. And why their Fourier series have nice properties is, remember, Fourier series is all about integration. The Fourier coefficients come about from integrals of the function with one of the basis functions, the cosine or the sine. Now, if we're dealing with, as we've introduced here, if we're dealing with an even function or an odd function, we've already said the cosine functions are all even and the sine functions are all odd. So if f is odd or even, then these integrands are going to be odd or even. It's going to be an odd or even function times an odd one here, an odd or even function times an even one here, and an odd or even function here. So the coefficients are going to come from integrating odd or even functions. If you go back to my two pathetic pictures up here, if you integrate odd or even functions along an interval centered at 0, as these pictures kind of are, remember, integration is about area under the curve. So if you're integrating an even function across an interval centered at 0, whatever answer you get is going to be equal to 2 times the result of integrating it over just the positive bit. Yeah? Because whatever area there is underneath the function over here on the right-hand side is replicated exactly on the left-hand side. So if you're integrating from minus pi to pi, it's equal to twice the result of integrating from 0 to pi. It's kind of easy to appreciate from the picture. On the other hand, if you integrate an odd function across an interval from minus pi to pi, what value do you get? 0. Because integration is area under the curve. For every positive bit of area you get on the right-hand side, you get an exactly corresponding piece of negative area on the left-hand side. And vice versa. This negative bit of area on the right-hand side, exactly corresponding to it, is an area of equal magnitude, but above the line. So a positive contribution to the interval. So when you integrate across an interval centered at 0, you accumulate a bunch of stuff up here on the negative half, but then you accumulate the exact opposite of it, positive and negative wise, on the right-hand side. So the whole thing, the whole integral will just cancel out. So an integral of an even function is twice, across an interval centered at the origin, is twice the integral across the positive half. The integral of an odd function centered at the origin is going to be 0. And that's going to very much affect the behavior of the Fourier coefficients. Okay, some of them are going to be 0, some of them not. So this is, okay, so in theorem 3.3 and on theorem 3.3, we just have the statement of those two properties about integrals. So G is even, H is odd. So the integral from minus t to t, g of x dx, this is going to be twice the integral from 0 to t, g of x dx. And the integral of the odd function is going to be 0. Now do we, okay, well, the proof we gave there based on just pointing to my pictures and trying to be persuasive is more or less the proof. So you can appreciate this from sketches of such functions. sketches of such functions, and integration as area under the curve. We understand integration like that. Which it is. But someone might fail to be persuaded by such arguments. So you can make them a little bit more rigorous. Can be made more rigorous using properties of integration and the defs of even odd, definitions of even and odd. So for instance, I won't give both arguments, but you just focus on the odd one. The odd one is the important one. The integral of an odd function is 0. So how might we prove this? Well, okay, all we know about the function h is that it's odd, and that it's possible to integrate it. So the first step would be to split the integral up. Okay. You want to integrate it from minus t to t. You integrate from minus t to 0, and you integrate from 0 to t. Now we're trying to prove this is equal to 0, so already it should be clear what we're going to try and do. We're kind of trying to prove that this is the negative of that. So when you add them together, you're going to get 0. And the fact that they're the negative of each other, you can kind of see where it's going to come from. We've got the opposite limits, one with a negative sign here, and we've got an odd function. And an odd function is all to do with how a minus sign, of the significance of introducing a minus sign into the argument of the function is. So we'll use a substitution. All of this is just effectively the rigorous technical way that you translate those arguments we were doing just from the sketches of such functions. We use a substitution, x equals the negative of t. So in other words, dx will be the negative of dt. And you just use that substitution on the first integral. You leave the second one alone. Now when x is equal to negative of t, little t will be equal to just t. When x is equal to 0, little t will be 0. Remember, x is the negative of, or t is the negative of little x. And so instead of h of x, we've got h of negative t. And instead of dx, we've got dt, but we've got this extra minus sign up there. Okay, so this minus sign here is present out in front of the integral. And the second integral, we're just going to leave that alone. Now, what can we do with this? So we can do a number of things here. But you just have to be careful. So a negative sign in this integral, well, that means I can reverse the direction of integration. And this negative sign, because h is odd, this comes out. So that's again going to be out here. So I got h of t dt plus the integral from 0 to t for h of x dx. So why is that true? So there's two moves that were made there in combination. Negative the integral from a to b is always the integral from b to a. And secondly, h is odd. So h of negative t is minus h of t. Okay, so I applied both those properties here. You can phrase it however you like. There's minus signs flying everywhere, but this minus sign, I can use that one to flip the limits. So that minus sign disappears. It's going to pop back out again because out of this one, h of minus t, h is odd, so the minus comes outside and continues outside to here. Okay? Or you can use the other minus sign to do the other job. It just depends how you tell the story. But this is the end point. Now, what are we looking at there? Now, this is something which sometimes people takes them a little bit to appreciate, but remember all these, in mathematics, the letters mean nothing. Remember, the letters are just names for the things, the real abstract mathematical objects that they represent. Okay. Here we're integrating functions of a real variable. This integral, okay, the fact that it talks about x is just immaterial. It could be your name, could be my name, it could be h of Killian, d Killian. They're just labels. What you're seeing here is the integral from 0 to some value, which is called t for some reason, integrating a function from 0 to some value. Here, the fact it's called t is immaterial. It means absolutely nothing. But you're integrating from 0 up to some value t, but it's the same value as the one mentioned over there, integrating h of t dt, just integrating the values of the function. Okay. But there's a negative sign in front of this. Okay. But on their own, those two integrals are exactly the same. These two integrals are exactly the same, but this one has a negative sign. So when you add them together, you get 0. So remember, variable names in themselves mean nothing. There are various traditions and conventions and normal practice around which it makes sense to follow. Just like it makes sense to drive everybody to drive on the same side of the road according to the direction they're going. There's no God-given reason to do that. Just it's a sensible convention. But if you're looking for why we drive on the left, you won't find it. You won't find a compelling logical answer to that question. It's just some arbitrary decision made along the way. And the same thing here. Why is a variable called x here? Why is it called t there? Well, it's just those are the letters I chose to write down. Means no more than that. Okay, so that's why the integral of an odd function along an interval centered at 0, so going from minus t to t, that's why it's always 0. Okay? And you can establish the other formula the same way. So you can establish the formula for integral of g the same way, using the same technique. Just doing this little substitution, introducing the minus sign into the argument for the integral on the left-hand side to make it comparable to the one on the right-hand side. So when you integrate an odd function, you get 0. So that has an effect on what the Fourier series are going to look like. Because the Fourier series, you're integrating the product of a function that's known to be odd or even, these cosines or sines, with your function f. So if your function is known to be odd or even, then these integrands will be one of the two, odd or even. And so one of these coefficients is always going to be 0. So that is summarized in the statements 3.4 and 3.5. So from theorem 3.3, we get theorem 3.4 and theorem 3.5. Now these don't require any more proof apart from the observation. So these just come from observing that if the function f is even, or accordingly odd, then the product f of x times cosine nx is also even or if f is odd, it'll be odd. And f of x sine nx, remember sine nx is an odd function. So if f is an even function, you multiply even by odd, you get odd function. But in the other possibility that f is in brackets odd, f of x sine x is going to be in brackets even. So if one of these integrands is odd, that means that coefficient, whether it be an or bn, will always be 0. Okay? So you get these two theorems that f is odd, sorry, f is even implies its Fourier series doesn't have any b's in it. Okay, the signs are absent from the Fourier series of an even function. And f is odd, that implies the reverse. Its Fourier series only features the odd functions. These kind of Fourier series get called cosine series. They've only got cosines in them. And the second type are just called sine series. They've only got sine. So these are termed cosine and sine series. And I think, we've proved all the ingredients there. It's just the observation about the behavior of these integrands combined with theorem 3.3. So if we're tasked with finding a Fourier series and we know our function f to be odd or even, this result can save us some time because we don't want, there's no point in evaluating an integral if you know it's going to be 0. So if you know that ahead of time, that can save you some work. So if you look at example 3.7, where we're considering the x squared function, okay, that is clearly an even function. Okay, it's x to an even exponent. This function doesn't care whether you give it 5 or minus 5, 6 or minus 6. It always spits back the same answer, just the square of whatever you gave it, okay? Which ignores the fact of whether the thing you give it is positive or negative. So this is an even function. So by theorem, whatever, one of those previous ones, so it has no sine terms in its Fourier series. Okay, by the previous theorems. So we won't waste our time in trying to find out what the coefficient Bn is because we know it to be 0. So that shortens it somewhat. So to obtain its Fourier series, we just have to deal with a's. So the a0 coefficient, and we can also somewhat simplify it now. We can just integrate from 0 to pi as long as we take twice the integral. Okay, using theorem 3.3, f of x dx. So this is 2 pi over 0 to pi x squared dx, 2 pi x cubed over 3, evaluated pi effectively. So this gives 2 over 3 pi squared. This is our a0. And the an's, the other an's, will be, again, I can just take twice the integral over the positive half, f of x cosine nx dx. So this is 2 over pi, integral 0 to pi x squared cosine nx. Now in the absence of formulae for integrating x cosine or x squared cosine, you'd have to do this as an example of integration by parts. Cosine nx is the derivative of sine nx over n. So the first bit of integration by parts would be x squared by sine nx over n, evaluated at 0 and pi. Then you'd be subtracting the integral from 0 to pi of the derivative of x squared, which is 2x, by sine nx over n dx. Now this bit here is going to give you 0, of course, because to evaluate this, we have to evaluate sine at an integer multiple n times pi, or sine at 0. But those are always going to be 0. So that square bracket there just comes to 0. So this, the integral we're left with, we can simplify it down a bit. We can take out the 2, take out the n. So we get minus 4 over n pi times the integral from 0 to pi of x times the sine nx dx. So if you're without the formula for the integral of x times sine x, I guess you've got to do integration by parts once more. Got minus 4 over n pi. Sine nx is the derivative of minus cosine nx over n. So in the first part, you get a minus x cosine nx over n, evaluated at 0 and pi. And then you plus, rather than minus, because the other term is minus cosine. The integral of cosine nx over n dx. Okay, what's happening here? Minus 4 over n pi. When you evaluate this at pi, so pi is going in for x, you're going to get minus pi cosine of n pi all over n. And integrating cosine, well, that's going to give you 0, because integrating cosine gives you sine nx over n, so that goes down squared. But again, you're just evaluating that at 0 pi. So again, that bit's going to give you 0. So you're just left with this here. So what have we got here? We got pi, canceling pi. We got n squared. We got minus, canceling minus. So you just seem to have 4n squared over the cosine of n pi. Cosine of n pi is well understood. Integer multiple of pi. Cosine of an integer multiple of pi is just odd or even, depending on whether you're looking at an odd multiple of pi or an even multiple. Remember, the cosine is the x coordinate. So if you've gone over the angle pi, the cosine is -1. But if you go over the angle 2 pi, you get plus 1. And every odd multiple of pi has a cosine of -1. Every even one has a cosine of +1. So this is just going to come to -1 to the power n times 4 over n squared. What is this thing we're looking at? This is the an. Okay. An coefficient from the Fourier series. There's no bn to find. You know ahead of time that this is going to be 0. The function f of x equals x squared is an even function. So this confirms the Fourier series that was given in the question. As x squared is a half of a naught. So a naught was 2/3 of pi squared. So this is 1/3 of pi squared. Plus the summation from n equals 1 to infinity. You've got the coefficient an, which is -1 times 4, -1 to the power n times 4 over n squared times the cosine of nx. Okay, so that's the Fourier series of the function x squared. Again, you can squeeze out. This has an interesting evaluation at 0. Very interesting evaluation at 0 when you evaluate the series. Okay, what's x squared at 0? It's easy, it's just 0. When you evaluate the right-hand side at 0, okay, you've got that constant term, pi squared over 3. Then you got this big summation, but if you're evaluating it at x equals 0, it's always cosine of 0, which is +1. So you're just getting this series here, which is very interesting, because this is 4 times the series of -1 to the power n over n squared. And that's a nice friendly series. That's the alternating series of the reciprocals of the squares of the integers. And if you straighten this out, we get pi squared over 12. Let's bring the pi squared over 3 to the other side, and you divide across by 4, so you get pi squared over 12. And then, see, this series begins when n equals 1 at -1. But because if you take minus pi over 12, the other side, so if you introduce an extra minus sign, it'll turn it into +1. So then it'll be 1 minus 1 over the square of 2, plus 1 over the square of 3, minus 1 over the square of 4. Sorry, 1 minus, plus minus, yeah, plus 1 over the square of 5, etc. It's 1 minus a quarter, plus a ninth, minus a 16th, plus a 25th, etc. And this series somehow magically is going to give you a 12th of the square of pi. Which is again very intriguing to see. Okay. Pi squared, remember, is the area of the unit circle. How is it that a 12th of the area of the unit circle is equal to the limit of that series? It's quite intriguing. Okay. We can track where it's all come from. It's all come from this, these orthogonality properties of the cosine and sine functions, the existence of these Fourier series, but it's quite tantalizing. Okay, we'll leave it there for now. I've seen you for a linear algebra lecture in an hour, and then again this afternoon.